I want to welcome you all. I am Liz Lieber. I'm the managing partner at Beyer Blunder-Bell Architects, and I'm a board member at Urban Green Council. And we want to welcome you to the second event in our panel series called Energy Upgrades in Historic Buildings. And today we're really excited to host representatives from the Metropolitan Museum of Art and the City of New York, along with the architects and engineers who make the challenges of reaching energy and historic preservation goals a reality at this iconic building. And without further ado, because we have a lot to go through today, I want to introduce you to a terrific set of speakers today, starting, of course, with our moderator, Madhav Munshi, an associate at Kohler Ronan Consulting Engineers. And thank you, Madhav, for being our moderator. I'm going to introduce our panel, starting with Brett Guyard, who's the head of Capital and Infrastructure Planning at the Metropolitan Museum of Art. Jasmine Rivera, the Director of Accelerated Efficiency and Conservation, which is the ACE program from DCAS. Eric Bodelson, partner at Kohler Ronan. David Mackay, principal at Kohler Ronan Engineers. Michael Whetstone, principal at Beyer Blunder-Bell Architects. And Henry Miller, our senior associate at Beyer Blunder-Bell Architects as well. And on to the presentation. Enjoy.
I'm Brett Guyard, and I'll give a brief overview of the museum and our institutional approach to energy upgrades. The Met is really a small city or village within New York City, and it sits on the equivalent of 4 city blocks within Central Park. It's comprised of 21 wings that are built over a 120-year period, and it's also one of the most visited museums in the world, with over 7 million visitors in 2019, and it's the home of approximately 1,600 staff. On a very busy day between Thanksgiving and New Year's, we can have upwards of 35,000 people in and out of the building on a given day. As an institution, we're not only tasked with curating and caring for our collections of art, but also our collections of buildings, which contribute to the history of architecture of the city, of the country, and of the world. Met Fifth represents over 100 years of architectural innovation, and the cloisters as well. And we're tasked with managing the change of these buildings over time. From 1880 to 2010, much of the work was really about expansion of our footprint within the park. But our current reality is different. And it's about addressing our mission, our urgent needs, as well as becoming a more sustainable building. And as we learned most acutely over the past few years, our institution also needs to directly address our current time and the climate crisis. Our buildings can be a protagonist in larger discussions about society and our relevancy as an institution within it, and we've coalesced around this idea at all levels of the institution. So rather than looking at our infrastructure as separate from our ambitions, we see that they're inextricably linked. So the Temple of Denver is as inspiring for its artifacts as it is for its structural achievements. And experientially, the skylights and sloped glass wall aren't separate from the art that they house. They create the entire experience. But these glass walls are also where we lose a lot of energy. So we've established and agreed upon 4 considerations for our planning and prioritization of all of our projects. And one of those 4 is to improve our building for future generations, to be resilient to the unforeseen and more sustainable for the future. And we have a lot of space to tackle these goals. We have 12 acres of roof alone, 35% of which are skylights, and we'll hear more about that later, and many of which are in need of replacement. Over the past decade, the Met has been striving to reduce our emissions, and we've seen measurable results. As of 2020, we've reduced greenhouse gas emissions by 33%, and we've saved over $15 million in energy costs. This will be described later in much more detail. Much of this work is enabled by our partnership with the city. And with that, I'd like to hand over to Jasmine Rivera to talk about that partnership. Jasmine?
Thank you, Brett, for that information on the Met. There's always something new to learn about that impressive complex. Thank you to Urban Green for hosting today and all of you who are logged in for attending, and a special thank you for the Met construction and engineering teams for all your work advocating for these projects and seeing them through. My name is Jasmine Rivera, and I am the Director of the Accelerated Conservation and Efficiency Program, or ACE, within DCAS DEM. The Department of Citywide Administrative Services, or DCAS, provides effective shared services to support the operations of New York City government. Its commitment to equity, effectiveness, and sustainability guides its work with city agencies on recruiting, hiring, and training employees, acquiring, selling, and leasing city property, and implementing conservation and safety programs throughout the city's facilities. Within DCAS, the Division of Energy Management, or DDDEM, is the hub for energy management in city buildings. DEM plays a critical role in supporting our agency partners' progress towards the city's major emissions reduction and energy objectives. These goals include a carbon reduction goal to reduce 80% of New York City's overall emissions for city government operations and the private sector by 2050, with interim milestones to reduce 40% emissions for city government operations by 2025 and 50% by 2030. DCAS DEM has partnered with the Met for the past 7 years by providing over $60 million in funding to support projects that will reduce emissions by over 7,000 metric tons of carbon dioxide equivalent. This work includes lighting, HVAC, control systems, and envelope upgrades. The Accelerated Conservation and Efficiency Program funds partner agency implemented capital projects that reduce emissions, energy usage, deliver cost savings, and provide other resiliency and equity benefits. ACE supported the projects being presented today through funding awards to support purchase and installation of HVAC equipment and building envelope materials. We are excited to be part of these upgrades for the energy efficiency savings, emissions reductions, and improved experience for those who visit. The Met upgrades supported by DCAS highlight the ability to improve energy and emissions performance during gallery renovations. This partnership benefits not only the art community, but the City of New York as well. I will now turn it over to Eric.
In 2013, the museum commissioned a long-term planning study that evaluated critical building components. This included MVP systems, elevators, the building envelope, glazed skylights, along with many other elements. The building systems were evaluated for remaining service life and prioritized for replacement. This graph represents various mechanical systems grouped into replacement need in 5-year increments. Highest priority systems are to the left, lowest to the right. The colors represent systems that overlap with a much larger transformational effort that would make sense to replace within that project, such as the systems highlighted in red. Those overlap with the ABC Skylights European Paintings project, and the systems highlighted in blue overlap with the Michael C. Rockefeller Wing project. As you can see, both projects were comprised of existing mechanical elements that required modernization. This was true for the glazing as well. Both projects we will discuss in detail further in this presentation. Once we had a good understanding of the condition of the building systems, we incorporated the many different building components into discrete and prioritized project groups that can be seen on this floor plan. The numbers indicate sequential priority, projects highlighted in red or high priority, blue moderate, and green being lower priority. The projects were estimated and a long-term plan was developed that was sensible for the Met to manage and finance. This spreadsheet is a snapshot that summarizes the resulting long-term plan, indicating a sequence of project priorities along with funding needs over a 20-year study period. Projects are listed on the left side and the approximate timeframe for completing the project is charted on the right. As a result of this process, the Met has completed many projects and energy initiatives in the past 8 years, with many being funded from ACE and Excel programs. David will touch on some of the projects and energy improvements achieved during this time.
Thanks, Eric. If you could advance to the next slide, please. As Eric was talking about with the LTFS cost model, we also developed an energy model during this process, a comprehensive energy model, going ahead and covering the full museum, all 21 wings, over 150 air handling units, and upwards of almost 1,000 thermal zones. So we created a calibrated energy model. Many of you may be familiar with what an energy model is. Calibrated energy model is a statistically significant, statistically valid representation of a building that uses historic utility data as a basis for validating the energy model. So we use that to develop basically a baseline of the existing conditions for the museum, and then evaluate some of these larger project groups in terms of area of opportunity, not only by end use, but also by location within the museum, and by program type as well. This way we can go ahead, determine what the carbon reduction potential is, determine what the energy savings potential is, and then knit in some of the energy reduction priorities along with larger capital project improvements going on simultaneously. We have implemented many enabling projects along the way. Since fiscal year 2013, the variety of projects having to do with, say, VFD retrofits on existing air handling units, trying to convert over to variable volume on the air side, also controlling water flows. Was basically everything in the museum, at the 2010 point, was basically a constant system. The building was on cruise control, and making any significant changes that would be reflected at the energy meter and by extension, reflected in the environment, would be quite challenging without doing some enabling work. Not only was that enabling work having to do with specific energy reduction projects, but the museum has a priority in terms of training personnel, in terms of, say, BMS operations, steam trap evaluation, proactive and preventive maintenance, and things of that nature, which really help to make sure that energy savings are achieved. These are some of the graphs that I was speaking to earlier. Kind of don't really need to spend too much time on those if you want to keep scrolling through. In the interest of time, we have a listing of some of the projects that have completed on the right here. As you can see, it's kind of extensive, but there's also a large variety, as I was speaking to earlier. And then you can see on this slide how the energy performance trends for the museum have been evolving. With that calibrated energy simulation, we developed a benchmark evaluating 5 years. That was 2006 through 2011. And we have data shown in site energy use intensity, or kBT per square foot per year. Our benchmark was 250 kBT per square foot, and we've been trending downwards steadily ever since, with 165 recorded in 2022. Just the fact that this building can turn down and achieve those levels of reduction is a major achievement, because everything within the building needs to basically be kept at very stringent indoor environmental conditions 24/7. So turned down in the traditional sense, or unoccupied in the traditional sense, does not really apply to the Met specifically. So we're very pleased to see these efforts showing up at the meter. And I'd like to hand it over to Michael.
Thanks very much. So we're going to give you a brief overview of 2 projects that we've done at the Met, both of which are in various stages of construction. The first one that you see here in the aerial view is the European Paintings Gallery's skylight infrastructure replacement, outlined in red. That's where the project is. It is actually the oldest wings of the Met. This is the way the Met looked in the late 19th century. Wings A, B, and C, we call them. You can see that the museum was originally in the middle of the park. Later on in the early 20th century, the iconic facade along Fifth Avenue was built. So these oldest wings have always had, occupying the second floor, skylit paintings galleries. You can see them as they were years ago. And our project was to, as has been done over the last 120 years, when in need, replace the skylights and the mechanical systems. Just to show everybody where that is in the museum, if you go into the Great Hall, entering the museum, there's a grand staircase that goes up to a beautiful Tiepolo oil painting at the top. Behind that is this enormous suite of galleries showing the European paintings. You can see here in this model, it's a total of 44 galleries, totaling 50,000 square feet. And all of those galleries are skylit and covered with 30,000 square feet of glass, as well as all the mechanical systems on top. And just to show you the basic way it works, here you see a typical gallery with a 20-foot ceiling. And the ceiling is made out of glass, and it's glowing because there is an even taller attic above the gallery. The galleries have glass roofs and a glass ceiling, and light diffuses in, giving a very nice diffuse light to the paintings, natural daylight being a critical way to show this kind of art. But one of the things that began to happen is that we have an antiquated skylight system of single glazing. The last one was installed in the 1930s, and we're trying to keep 70 degrees and 50% humidity in the galleries at all time. So there's an enormous problem with not only heat loss through the single glazing, but trying to prevent condensation. During the winter, when the glass gets cold, water tends to form on it. And so the way that the museum had to do this previously was to heat the attics to more than 100 degrees all winter long, so that the condensation wouldn't form at an enormous loss of energy and heat. In addition to that, the HVAC systems were overtaxed, and sometimes the steam reheat coils would spring leaks, and it was just a complicated problem that called out for a kind of a comprehensive solution. The skylights that we are replacing were built in the 1930s. You can see it's corrugated glass, single glazing, overlapped like ships lapping. Unfortunately, although it's very durable, it's terrible for condensation and air infiltration. So we doing a comprehensive replacement with really the best, long-lasting, most efficient system that we could find. So this is being replaced with a laminated glass with a frosted interlayer with silicone glazing attachment. And the silicone glazing is attached in the factory to a metal cassette, which is attached to the framing. And then the framing itself has an integral extra drainage system so that any water that gets through flows into these channels and flows out. And the idea that this is the most maintenance-free, efficient, long-lived system that the Met could possibly put in. We also had to put in a series of sun-controlled louvers. So on the underside of the glass are louvers that are manually controlled so that the curators can control the amount of light entering each gallery. Eric will talk about the engineering.
So as part of the skylight replacement project, it provided a much needed opportunity to modernize the mechanical systems and distribution elements in the attics that were over 50 years old and configured poorly. The floor plan on the left, go back, Michael, please.
Sorry.
The floor plan on the left represents the original condition with the green highlights indicating VAV box locations. And the floor plan on the right indicates the final design condition to be completed later this year. As you can see, we significantly consolidated mechanical equipment with the large colored boxes in the center of the plan being air handling units that were replaced as part of this project. Highlights of the improvement include removal of reheat water piping over the galleries so that only air ducts will be in the attic going forward, equipment consolidation to waterproof central mechanical spaces, detection and protection if systems fail. For instance, if a leak is detected, a sequence is initiated to shut down the pumps, close off the valves to the water systems that feed all the VAV boxes, and it allows the Met to react in a timely fashion without introducing a flood threat. And the ductwork was configured to allow for improved daylighting. The team went to great lengths to study and position the ductwork for optimal gallery lighting. Additionally, we were able to improve the conditions both in the galleries and the attics while improving energy performance. You can see the section on the left indicates existing conditions at the European Paintings Galleries attics. The primary means for controlling condensation, as Michael indicated, was through superheating of the attic, generally around 100 degrees. This large temperature discrepancy between the galleries and the attic would compromise the gallery conditions below, and also contributing to the issue was pressure differences in the attic at the ley-like boundary, forcing some air in some instances up into the attic and in some instances down, that heated air down into the galleries. The section on the right indicates the new design conditions. We were able to substantially reduce the heating requirements throughout the vast attic while still controlling condensation. This was achieved with, first and foremost, the improved skylight glazing and framing system Michael discussed, as well as active moisture monitoring of the dew point with corresponding variable supply air temperature and air pressurization control between the attic and the gallery conditions. Next slide, please.
There we go.
Desiccant dehumidification systems designed to dry out the air supply to the attic, seen in the graphic to the right, vastly increasing the dew point temperature, was also a significant improvement in the attic space. And we also ducted dry air to all glazed surfaces in the attic, as can be seen on the graphic on the left. This ensures dry air moving across the glass, preventing condensation from forming. All of these measures resulted in a substantial energy improvement from the previous approach. Next slide.
Yeah, and as Eric mentioned, there were several different things contributing to this energy reduction. Majority of which had to do with reducing the operative temperature in the attic during winter. And what enabled us to do that was to use the desiccant system to dry out the attic such that our dew point was high enough, low enough not to have condensation occur. What you could see in those couple charts that were on the previous slide is compared to a replacement in kind code compliant baseline that we worked out with DEM and DCAS. It was about a 33% reduction. When you actually compare this to what the actual conditions, the actual usage was for ABC skylights in the gallery areas, it was more close to an 80% reduction versus actual conditions due to the brute force heating that had to occur above the galleries themselves. So a significant reduction in carbon dioxide and also a significant energy savings. But in the interest of time, you can move on to the next project we want to highlight, Michael.
All right.
I think we'll hand off to Henry.
Yeah, well, to one more slide. So this project is been under construction for a number of years. The first phase was completed, I think, in 2020, and the second phase will be completed, I believe, later this year. And you can see some of the new skylights, the new attics with the new skylights and the sun control system, and then one of the new galleries with the improved daylighting and HVAC system. So on to Henry Miller and the next project.
Thank you, Michael. So next up, we'll look at another project which is kicking off at the Met. This is at the Rockefeller Wing. And the scope here is a gallery renovation, an HVAC systems upgrade, and also the replacement of this large south-facing sloped glazing, which you see in the picture here. I think interesting, picking up on some of the things Brett said about the age of the museum and the range of technologies, architectural technologies we have here. The project Michael showed before, that was a 1930s skylight system, which has reached the end of its technical lifespan. This is a 1980s skylight system, sloped glazing system, that similarly has reached the end of its technological lifespan. We see some of the conditions in the gallery space and at the exterior deteriorating. Films on the glass, shades that are deployed at the interior at all times, trying to deal with what is a tricky situation of glass south-facing in a gallery space. So we had the technical requirements of energy performance, but also some gallery performance requirements as far as daylighting levels as well to deal with this sloped glazing wall. This is a slide that just shows the interrelationship between those pieces which I mentioned, the gallery space, which is really the full 40,000 square feet of the first floor of the Rockefeller Wing, the Michael C. Rockefeller galleries, which will be renovated, the sloped glazing wall, and then the HVAC air handlers and mechanical room, which is to the south in Wing P. So all of those systems will be upgraded as part of this project. From the exterior, this this is a landmarked building. This is a landmark issue. So we did go through a lot of iterations of the design to make sure we were adhering to the context of the building and the precedent set by previous architects. The architect of this wing being Roche Dinkerloo. We did, however, want to reduce the amount of joints by increasing the glass light size. That's both for efficiency, but also for energy efficiency, but also for better views out to eliminate some of the mullions that obscured the view. An important piece of the design requirements from the museum side were to allow a view out into the park, which had been obscured by the shading and the films that I showed in the previous slide. Looking then just a little bit at the glass system in this case, and how it's been kind of engineered to perform thermally, but also as a daylighting control measure. This section on the left shows the solution that we arrived at, which was to gradate the amount of light that came through the glass at each row as you go up, so that you have the view out at row 1, and then you slowly tune the amount of daylighting allowed into the gallery space as you go up, so that you're not exceeding the daylighting requirements that the art has, and requiring close coordination with the curators and the conservators on the Met side, and with Arab as a daylighting engineer and facade engineer. In this case, you can, and then on the right side, you see the pattern of the frit that we arrived at, which is gradated, as I mentioned. In the middle, we have a triple IGU with laminates on both the inner and the outer lights. This gave us a lot of opportunity to modulate the quality and the amount of light with translucent frits or translucent interlayers and frits. And the glass in this case is right at the gallery, so the aesthetics of it is also extremely important. We opted to go with a triple pane IGU for this project. We had looked at that as well for ABC skylights, but the strength of the existing structure actually precluded the additional weight of the triple pane. So here we were able to deploy that. So this is heading into construction now, but wanted to show a photo of the process that we go through. So on the left is the existing condition, and on the right is actually a scaled mock-up that we built of the future gallery space, really underlining just how critical being able to model and measure the performance of the system is before you install it, both aesthetically but also performance-wise. So it's an exciting process as you go through and kind of confirm some of your assumptions, and then work through modeling up to the real thing. Looking at the systems, both what's there now and what we're proposing. What's there now is a insulated pressure cap system, state of the art in 1980, 1982 when it was installed, versus the face sealed cassette system that Michael described. So it's really the same system we deployed for ABC skylights. all the things Michael mentioned about longevity, thermal performance, belt and suspenders drainage, we did here as well. Looking a little bit at the modeling, so working with the whole team to do therm modeling to confirm where the dew points are in the glass, and again, this is right in the gallery. It's the south wall of the gallery, so issues of condensation were critical. Making sure that we wouldn't have any sweating of the glass, and then also, because this is sloped glazing, an interesting kind of property of the geometry is that the convection loop that's set up in the interstitial space between the lights of the IGU actually short circuits as you rotate the glass into a sloped condition. So you can see that in the diagram in the upper right, and actually, transfers heat across that gap more efficiently in a sloped condition. So, again, something we had to account for, something that triple pane IGUs help with, but another kind of indication of the amount of analysis and modeling that's required to make sure we get what we want. And with that, I'll hand it off to Colaronen.
Yeah, and similar to what Henry was talking about with the convective loops changing within the glazing system itself when it's sloped. If you go back to that previous slide, please. We wanted to also ensure that our HVAC distribution would go ahead and get along that entire sloped curtain wall. We really only had 2 existing points to distribute air from. So we were able to use computational fluid dynamics to look at different velocity profiles, different temperature profiles, and see what we would need to do in terms of sizing of the system, but also the velocity of the air that we delivered and the angle we delivered it at, to make sure that the glazing surface was a consistent temperature throughout that high elevation with that sloped condition. I think Eric might want to speak a little bit as far as the mechanicals go.
As Henry mentioned, the project also provided the museum with the opportunity to improve mechanical system support in the MCR wing. You can see the location of the equipment directly adjacent to the wing in the graphic on the right. Some of the highlights of the upgrade include replacement of 4 constant volume air handlers with new variable volume custom units, including efficient fan arrays, and that was about 300,000 CFM in total, a pretty substantial number. And when you're working in a building like this of a historic nature and it's constantly occupied, phasing always becomes a challenge. So we created a way to creatively phase the 4 air handling unit replacements so we can utilize units that are serving vacated spaces to temporarily serve occupied spaces. This eliminated the need for the installation of temporary equipment and services in the center of the building, which would have been a substantial challenge to facilitate. Modern controls were employed, allowing for turn down, chilled water load matching, and enhanced ventilation strategies, and as well as some steam upgrades, piping distribution upgrades, new preheat coils, new pumps, a lot of aging equipment that was really contributing to a poor energy performance previously, and gives us an opportunity to move forward with modern equipment performs much better. When complete, this new equipment serves about 100,000 square feet of galleries, art storage, and again, it has a very substantial energy performance improvement for the wing.
So with that, we'll just leave you with a slide of the proposed rendering from the south for the Rockefeller Wing. The construction is kicking off this month. I think the CM is starting to mobilize. So this is kind of the future of the south view of the Met. I think with that, we're done.
Yeah, so if all of you can help us starting your video, and Madhav will help us moderate the conversation, and he will also raise the audience's questions.
Thanks, Viri. I'm unable to start my video. Maybe you can enable that, but I can get started. Oh, great. Excellent. Thank you to all our presenters for such insightful and detailed explanations on the challenging projects that you're working on at the Met. My name is Madhav Munshi, and I'm an associate Kohler Ronan, and I'm also an active member of the Programs Committee of the Urban Green Council. I would like to start the discussion by asking a few questions and turn over to the audience for theirs. It was really great to see that the museum had started tracking and reducing carbon emissions earlier than most of its peers. And for a project of such monumental scale and complexity, I can imagine it takes a lot of work to make anything happen, or even just to get started. So my first question is to you, Brett. How does the Met navigate conversations between all its stakeholders, internal and external, with curators, conservators, landmarks to balance sustainability, preservation, and conservation issues? Could you speak about that a little bit?
Sure. Thank you. I think part of my answer is that we rely heavily on our consultant team to help us do that. But one thing we do is try to use the construction department at the Met as the consolidator of all that information, so that we can speak with one institutional voice. I think if you, as Henry knows very well from working on the Michael C. Rockefeller Wing project, some stakeholders would probably design a dark box with 70-50 humidity with no visitors, right, to protect the art. Right. A curator may say, actually, some of this collection needs to be outside, so we don't even need climate conditions at all. And then landmarks may say to us, you need to keep that glass. It's a part of the history of modern architecture in the city, but it's a south-facing glass wall with light-sensitive art on the inside. So we have all of these different voices, and we need to listen to everybody, because everyone together then leads us to a solution that works, and be willing to iterate through it. So I think part of the way we build consensus is by working through multiple options, some of which privilege other things, one thing over another. And then we kind of land on a solution. I think the risk that we face is landing on a compromise, right? That isn't satisfying really to anyone and kind of looks like a compromise. I think that's why the ABC Skylights project and the Michael C. Rockefeller Wing have been so successful, because through the kind of technical iterations, they've actually invented something rather than just kind of compromise a solution that takes a little bit from everyone. So it's a challenging project, but it's also really exciting because you're hearing from experts in their field. It's just a variety of different fields and trying to bring it all together.
No, that's great. And I assume that when all these projects are being implemented, design, construction, the Met never shuts down, right? It's always a building that's operating continuously, the visitors in, and like David mentioned, it's always maintaining that constant temperature and humidity conditions. How does that happen? Like, how do you enable construction projects? How do you keep the museum going and operating at the same time? What are the logistics involved with making that happen?
Well, maybe I could speak to the operational side, but I think it would be good to hear from Mike or Eric about specifically ABC Skylights, about how they enabled that project to happen. I think from an operational side, in a way, we're lucky because we have a really big museum. We have lots of elevators, we have lots of stairs, we have lots of places to eat, we have lots of bathrooms. So shutting down, an entire city block doesn't mean we're shutting down the museum. So we're able to keep functioning, keep art moving, have options for our visitors. So I think operationally, while it's challenging and we don't want to have multiple projects going on at a time that shut down large swaths of public space, we are able to keep going when we shut down, for example, an entire wing. I don't know, Mike or Eric, if you want to add about some of the enabling work specifics for these projects.
Sure. I would defer to Henry to answer that, and Eric.
Okay.
Brett, I think, it kind of, as you indicated with the design and planning process, it's really about teamwork. each of these projects has a construction manager that comes on board. There's a lot of planning for the design, but also for the implementation, phasing, temporary walls, temporary control of HVAC units, and then on the Met side, art movement, things like that to make sure that that's prepared in advance. It is quite a choreography, in each project because of where elevators are and art path movements. It does require specific logistical designs. And I don't know, Eric, from the mechanical side, working with the engineering department at the Met, there's always aspects of that as well.
Yeah, I mean, like Henry mentioned, it's teamwork. We create phasing logistics plans with the CM. We worked with your engineering team, Brett, at the Met, and every project has a different scenario that needs to be dealt with. And for instance, on ABC Skylights, there was one gallery that had leather walls that couldn't be relocated. So that environment needed to be maintained in the center of a construction project. So not only did Henry's team need to create a way to make a box that was tight and clean, we had to temporarily condition that space, and the CM came up with a solution that we worked with them on, and that was a one-off that just seems to happen with any project that you do at the Met. There's always a scenario that you have to accommodate and figure out a solution to, and as long as you work as a team, we can solve any of these issues.
That's great, Eric. Thanks for that. Thank you all. Sorry, did anybody want to add? Okay, so I'm going to take one audience question. I guess everybody wants to know, how is the Met approaching Local Law 97, and is it covered by the law? Maybe Jasmine, Brett, do you guys want to sort of tackle this one?
I'm happy to take it, Jasmine. Anyone on this can correct me. I think it's nuanced. So I just first want to say, I think the important thing to the Met is what we talked about earlier, with the building being a protagonist in these conversations. So kind of regardless of being the nuances of Local Law 97, it's important for us to address these issues regardless of what laws there are. I think Local Law 97 says that city-owned buildings are looked at as a whole, and as a whole, there's a need to reduce 40% emissions by 2025. The Met is obviously one of the largest, so it's really on us to do our part to support the city in achieving that goal. It's not so much about like, would we be penalized or not, but we see ourselves as an institution where we do something and others tend to look to us to see what we're doing. And so we feel that we're a leader. I don't know if that totally answers the question, or Jasmine, you have anything to add to that, but that's our general take on our approach to Local Law 97.
I thought that was a pretty comprehensive answer there,
Okay.
Brett. As a member of the Cultural Institutions Group, Local Law 97 doesn't specifically apply. However, as Jasmine outlined before, the city has greenhouse gas reduction aspirations that the Met has definitely signed on to, and we want to align performance with the city's long-term goals. And we've made significant progress towards that, and we're getting towards that interim goal, that interim 2024 goal of a 40% reduction, and we'll keep on fighting to get more reduction. The biggest challenge leading ahead is that the museum's still very dependent on steam. We still are very dependent on high temperature hot water. So maybe some of the other things, the other conversations that would work with Local Law 97, like moving over to electric-based heat pump systems and things of that nature. There is some opportunity for that in the future that we're exploring, and there will be significant greenhouse reduction potential from those, but it's not specific to Local Law 97 as much as just making sure that we're at the forefront of achieving and joining on to the city's overall goals.
And I concur with everything that was said in response to that. Yes, the Met has been a great partner and is part of the Cultural Institutions Group and actively looking into different feasibility studies of how to address the energy sources that David pointed out, and looking to meet, if not exceed, the goals where possible based on the constraints that Brett mentioned of the historic integrity of the building, the art, protection of artwork. So there are various constraints. However, the Met has been a great partner in looking to achieve these goals and also to share this information in forums like this so that way others can learn from this experience.
That's great. And Jasmine, like just a quick one, like who can qualify for funding from the ACE program? You know, is there, and is it pretty much any historic building or is it specific projects?
It's specifically tied to city buildings and properties where the heat, lighting, and power budget is paid for by DCAS. But if anyone is interested, they are welcome to contact me directly and we can talk more about their specific situation and eligibility potential.
Okay, great. One of the questions that's come through is, what measures did you guys find had the highest impact on carbon emissions reduction? And how did you go about verifying those savings? Anything that stood out as a measure, or yeah?
Oh yeah, I guess I'll field that. It really depends on the project. You know, but overall, if we're talking about, say, ABC, which we highlighted specifically today, I think you really got to look at this as integrated energy conservation measures that work together. It's a holistic combination of things that interact with one another. You know, from an energy standpoint, how do you reduce condensation risk? And how do you lower the attic operative temperature and save energy? And we approach that by improving the envelope, not just the glazing, but also the opaque areas, and then going ahead with something unique. I mean, I'm not aware of any attics that have desiccant systems above galleries. That is, you know, a pretty unique way to make sure that we don't have to put input energy into the building. So, you know, it's the way that all of those came together to make sure that the condensation risk wasn't present that led to such a large greenhouse gas reduction. And you know, it's also a moving target too, because as I'm sure everyone's aware, or anyone who's intimately involved with greenhouse gas emissions in the city, coefficients change every year, and you know, our electric grid has been making significant improvements, and the greenhouse gases associated with those have been going down. So, you know, the electricity we saved, you know, 10 years ago and are currently saving today doesn't save quite as much greenhouse gas emissions as it used to. And now, you know, something like improving or reducing steam is much more beneficial in terms of an absolute greenhouse gas reduction. So it's, you know, it's a little bit difficult to put it on one measure.
Of course, yeah.
But I would like to reiterate that, you know, it's a comprehensive approach to measures and how they interact that ends up having the biggest return on investment, not only financially, but in terms of all that stakeholder interaction, all that extended design time and extra analysis to make sure it's actually captured. And then I would put in a plug for commissioning to make sure that, and commissioning and measurement and verification, you know, to make sure that the final product ends up fulfilling the owner's project requirements, and that those greenhouse gas reductions and energy savings actually show up at the meter, which is, you know, a challenge in and of itself.
So, thanks for that answer. Could you explain the upgrades to the BMS systems, if any, and would you call them an intelligent building in terms of automation?
I'll field that one, Matt. So, you know, we've been upgrading the control system throughout many of these projects that we start, and And I would say that, within the last 10 years, they were still operating with a lot of pneumatic control systems in the building. And recently there has been a substantial improvement in the controls. So, I would say as far as it being an intelligent building, it's they have control of every system. They have monitoring of every system. Where they fall short a little bit is on the integration of the controllability of a lot of these systems. So I would say, we're halfway there to a very smart building. And what what we try to do is introduce another level of controllability to the systems that we employ. And that means, for instance, on ABC skylights, whereas in the past we would have constant volume systems that would try to maintain that tight control of 70-50 temperature and humidity requirements, now we're able to turn those systems down at night and still maintain those temperature and humidity requirements, but we can watch it and we can learn over time how the system reacts, and then we can adjust the controls accordingly. So that's how the smart building aspect comes into play in these projects that we are undertaking currently.
Thanks for that, Eric.
Just to add on to that,
yeah.
just a touch if we do have time. In terms of the evolution of the Met, we're starting to incorporate a lot more into the building management system in terms of measurement and verification or sub-metering. We ported over and got rid of all pneumatic controls, which means that we know how the systems are operating in terms of temperatures, humidities, things of that nature, but actually collecting data and bringing it back in terms of the energy usage for the individual systems is something that's recently just been coming online over the last few years and moving towards that intelligent building that you were speaking towards.
Cool. Definitely, I'll ask a question to Michael and Henry, and also Brett. As a historic building, what challenges does the Met face when making such significant decisions about its building to operate more sustainably, and also, how are the historic character and historic building requirements upheld? While all the glazing stuff is going on, all the roof replacement and the skylights, how do we do that?
I can talk a little bit about that, since we got Landmark's approval for both of the projects that we showed you, having to do with the glazing replacement. And one thing that we tried to do is say that a skylight system built in the 19th century and one built in the 1930s and one built in the 1980s, they all look different because the technology of glazing keeps evolving. So we approached the Landmarks Commission and said, what we think is historically appropriate is that the Met always have the best possible glazing system, even if the look changes. And to support that, we actually found a drawing of McKim, Mead, and White from 1907. They replaced the skylights in the Great Hall 125 years ago. And a note on the drawing said, "Skylight details shall be similar to this or the best possible quality." And so we tried to use that to argue that the intent was not that the specific skylight be there, but even the original architects wanted something that was the best possible system. And that's what's appropriate. And the Landmarks Commission actually took us up on that. And in the approval for the ABC skylights, they actually said that we understand that the technology of glazing and the details and the sizes of the panels changes from time to time. And that's part of the history of the Met. And therefore, it is appropriate. So we felt like that was kind of a very successful argument to make, because we were able to get systems that look very modern and very different than they did originally on both of those projects.
I'd also add that there's something to be said from a sustainability standpoint with keeping existing buildings and utilizing the embodied energy of that building fabric. So that does kind of go both ways as a preservation and sustainability benefit. So
that's great. Now, I know we're running just 2 minutes left. So one final question. I know it's probably the most loaded question. What advice can you give to other institutions with historic buildings in their portfolio who want to reduce their carbon emissions? What should be maybe the first 2 or 3 steps that they should start thinking about? Brett, do you want to take that on from the owner's perspective?
Yeah, I can take that in general terms. I think the first is to acknowledge that climate change is real, that it's happening right now, and that buildings are protagonists in addressing climate change, and that as a large building owner, you have a responsibility to act, and then getting institutional commitment all the way through the organization that this is important, so that then when projects come up, there's in a way like a firewall where they don't get through unless they're starting to address these issues, so that we're committing to the kind of urgency of our current time. I think that level of consensus is really important, because it's very hard to pick apart an argument for doing a project like the replacement of the sloped glass in the Michael C. Rockefeller Wing if everyone agrees to that as a premise. So I think from our perspective, it's really important to have buy-in that the building is important in addressing these issues, so that you can't value engineer out the replacement of the glass, that it becomes linked to the project. So I think from our perspective, that's something that's really important. I think I don't know if others or the BBB team want to address that too from their perspective.
Envelope and HVAC. I think those are.
Yeah. And also, I just want to make one final comment. Local 97 doesn't really have any exemptions. So, and even at the Met, they have their own. They're actually complying with the New York City compliance requirements, which are actually quite more aggressive than the rest of us. So, the work that you guys are doing, the effort that has gone in is quite phenomenal. So I think we have to close out, unfortunately. I would really like to thank Brett, Jasmine, Eric, David, Michael, and Henry for this informative and exciting discussion. Today's example is a good example. Today's program is a great example of the work we do at Urban Green. We take on the biggest challenges with the biggest solutions to have the biggest impact. We do that through our 4 key activities. We convene, research, advocate, and educate. So thank you so much for joining us today. And thank you for spending time with Urban Green today.